In this video, I'm just going to go through the basic process of using Simulink within MATLAB to build a model for investigating quadrature amplitude modulation, as you'll need to do for the completion of the assignment. All right, so some of you will not have used Simulink before. So the first thing obviously you need to do is if you haven't already done so, is download and install MATLAB. As most of you probably know at this stage, there's a license available for any registered NUI Galway student to download and set up MATLAB on their own computers. The one warning I'd give, having gone through the process, is don't just select all toolboxes. You'll end up with a huge image that you're trying to install. So be selective. I assume you'll be able to uninstall or install anything you need to that you missed your initial install. You can do it later. You'll need a communications toolbox and block set to do this particular assignment. Okay, so to start the process, particularly if you haven't used Simulink before, just click on New, go down to a Simulink model, and go to the communications toolbox and click on the create model option there. Okay, so that'll kick off the process of starting up Simulink. It just takes a couple of seconds, sometimes a bit longer. Okay. All right, so Simulink is now open. You basically start with a blank canvas. All right, so now to the aspects that are specific to this particular assignment. All right, so in order to do this, we're going to build a model of a very basic QAM transmission system so that we can investigate the impact that the energy per bit over noise density, or the power efficiency, has on the likely bit error rate. And this allows us to run a simulation and compare it to the theoretical results that can be got by applying the equations that we did in lectures. Now, in order to build a simulation model for this, we need 4 basic components, which we'll go through now, and then we'll apply some visualization and instrumentation tools that just allow us to get a better feel for things and to measure quantities. Okay, so the first block we need to apply is a block which is capable of randomly generating symbols that we want to transmit. Okay, so you click on the library browser. If you go down then to, I'll just close that particular one for a minute. We open up the communication toolbox. Okay, go into the communication source and random data sources. You see there's 3 different options. The simplest one that we want to use here is this random integer. Okay, so this block, you can then drag and drop it out, drag and drop it out here, is, as the name says, it's a random integer generator. So it's going to randomly generate integer values. Okay, we'll look at how we're going to use that in a second. The second of the blocks we need, and the last block we'll need, and we'll come back to the one that's in the middle, are the actual QAM blocks themselves. All right, so we need to add a modulation, go into digital baseband modulation, and down to QAM. Now there's a number of different options here. We're going to use the rectangular QAM modulator and demodulator. So I drag out again modulator one, and if I go back inside, and I'll drag out on this side the demodulator one. So let me just bring them over here. All right, so our modulator, as the name suggests, is going to simulate. Now it's not a simulation in the sense of actually generating the modulated waveform. Okay, it's kind of a very rough and ready modulation simulator in the sense that it'll generate a representation of the in phase and the quadrature amplitude. Okay, we'll come back to that in a second. As I said, there's a 4th component, and that is the component which will simulate the behavior of the communication channel. Okay, so whatever sits between the modulator and the demodulator. And we're going to stick with what we looked at in lectures. Okay, so we go to channels, and we'll see here in this case we're going to be using the additive white Gaussian noise channel. Okay, just as we looked at in lecture. So again, drag and drop it out. Okay, we can align it up here. All right, so we have the four components now. The three core ones are the modulator, the channel, and the demodulator. Okay, so the modulator will take in effectively a sequence of random integers. It'll convert each of those random integers into a representation of the modulated waveform. Okay, now the representation that Simulink implements is basically the amplitude of the in phase and the amplitude of the quadrature. Now internally it represents that as a complex number, okay, where the real part is the in phase component amplitude and the complex part is the quadrature amplitude component. Okay, we'll then pass that sequence of representations through the channel model, which is just the additive white Gaussian noise channel. And then we have the demodulation one, okay, which takes the noisy version of the modulated waveform. Okay, so it's a noisy version. It's a complex number, which is the original transmitted complex number representing the transmitted waveform with noise added into it. And the output of it, again, should be an integer value. Okay, and if there is no errors in the system, then for every integer value which was fed into the modulator, we should be getting the exact same integer value coming out of the demodulator. Okay, so that's the basic idea with this simulation model. Okay, now as I said, it's not an exact replication of the modulation process in the sense that we don't actually generate any sine waves or anything like that. It's as it were almost a shorthand version of the modulation process. Now, the next thing we need to do is we need to connect up the blocks, and then we need to configure them, and lastly then we'll add our instrumentation. All right, so our random integer generator is going to be generating a sequence, as the name says, of random integers, and we want those to be fed into the input of the modulation. So we just drag and drop the arrow there. Similarly, we want the output of the modulator to be fed into the input of the channel. So you can either drag from left to right, or as I'll do in this case, I'll drag from right to left. Okay, and the output of the noisy channel is to be fed into the input of the modulator. Okay, and then we have the output of the modulator, which we'll come to in a second. Okay, so firstly, we're going to start with 16 QAM. So the modulation process has 16 possible modulated signals. Okay, it's a constellation diagram we'll come to in a few minutes, but has 16 points in there. Okay, so what we want with our simulation process is that our random integer block here just goes through a process of randomly generating values between 0 and 15. So 16 possible random values. Okay, and we will run our simulation through a large sequence of generating those random integer values. So the first thing we want to do here is we want to configure our random integer generation. Okay, now the only quantity here we really want to change here is the set size. Okay, so as the description tells you here, okay, it's this block randomly generates using uniform distribution integers in the range of 0 to m-1, where m is the set size. So in this particular case, because we are simulating 16 QAM, we want our simulation to go through the process of randomly generating values between 0 and 15, all 16 possible values. All right, so the only value in this configuration for the random integers we need to set up is the set side value. We want 16 values, okay, 0 to 15 to be generated, so that our simulated modulator is being driven by all 16 possible values that it can handle. So, okay, we apply that, okay, and okay. If we go into the modulator, then, okay, if we look at the various values here, firstly, it defaults to 16, which is the value we want, 16 QAM. Okay, the input type is integer, and the main thing we want to do here is, yes, we want to use gray codes. I'll explain why we want to use those in a few minutes. We'll change this to peak power. Now, the only thing is, if we change that to peak power, we have to use the same thing. This is about the scaling, really is about the scaling of the signal power. Okay, and if we do this in the modulator, we also have to do exactly the same thing in the demodulator. Okay, so if we apply that, okay, and we got to make sure the demodulator block's exactly the same. So I'll skip over to the demodulator. So again, 16 is correct. Just it is 16 QAM demodulation. It's grayscale. Output will be integer. Okay, because again, remember our input is to the whole process are random integers. So the output will be integers. And as I said, we just got to make sure that we change the configuration here of the normalization to be the same thing. So again, we'll apply peak power. Okay. So that's the modulator and demodulator. If I click on the Gaussian noise, all right, so this will randomly add noise corruption only, no other form of corruption, to the output of the modulator. And it's a random process, so we have to indicate an initial seed. The mode of operation we want is signal to noise ratio. Okay, energy per bit over noise density, exactly as we had. Now we start with a pretty high energy per bit to noise density. So there should be, relatively speaking, not an awful lot of noise added in. Now, the one thing we do have to change here is the number of bits per symbol. So it's 16 QAM. So every symbol represented by 4 bits. Okay, 2 to the power of 4 is equal to 16. So we need to change that. All right, that's to ensure that the right amount of noise is added in here. We've indicated the energy per bit, okay, over noise density. So we need to basically indicate how many bits make up a symbol, okay, because the QAM will be generating an output per symbol. This is adding noise into it, so to get the right amount of noise, we need to combine together both the energy per bit information that's configured and the number of bits per symbol. Okay, so that's the last block that we need to configure. All right, so that's the basic model that you're going to use throughout this assignment. Now, we want to visualize what's going on here, and we want to collect some data as we run our experiments. Okay, so we're going to use a few more blocks, okay? The first thing I want to do here is I want to look at constellation diagrams of what is actually being transmitted. Okay, so I want to add a block which will generate a nice simple visualization of constellation diagrams on both the transmitted and the receiving end. All right, so again, I click on the library browser and if I click on the comms sync, so a sync, you'll see constellation diagrams here. So I'll just drag that out. Okay, and I want one for the transmitted signal and one for the received signal. So I'll bring 2 out here. Okay, so I'll just place them there. Let's reline this a little bit. Okay, so these are just going to allow me to visualize. They'll generate a nice little graph, or not a graph, a plot of the constellation diagram. And this one is going to be for the transmitted signal. I'll put that there. And this one will be for the signal being received. Okay. Now, just when we run the simulation, we'll see a MATLAB plot window will appear with these 2 constellation diagrams. Now, by default, those 2 windows will have the same label on them. So just to make the labeling a little bit clearer, okay, what I'm going to do is I'm going to rename this the transmitter constellation diagram. And again, by just clicking on the text there, I'm going to rename this one the receiver constellation diagram. Okay, and just get rid of that character 1. All right, so that's just going to be a nice little visualization tool. You can copy and paste some examples. We'll look at them now in a second. Now, the other important thing throughout this assignment is that you will be interested in looking at the impact which the amount of noise that the channel implements has on the error rate. So we want a block that will allow us to calculate the error rate, and we want to have a quick way of accessing the information every time we run a simulation. Okay, so again, we have inbuilt blocks that will do that for us. And again, you open up the library browser, go to the communication toolbox, go to the same one we had open a few moments ago for the constellation diagrams, which is ComSync. And see, we have this error rate calculator or calculation. So again, grab it, drag it out. Okay, and we just realign it here. Okay, so this will be used to calculate an error rate. Okay, it has two inputs because it basically compares two sequences of values. Okay, a received and a transmitted. So it's comparing what's received to what was transmitted. We are going to compare the received sequence over here, which was used to drive the modulator, to the output sequence over here, which is coming out of the demodulator. So we essentially, when we run our simulation, this is going to be the core calculation block of how many of the received integer values are the same or are different to the integer values which were transmitted, or basically being used to drive the transmission over here. Okay, now if the noise is low enough, they all should be the same. Okay, every integer value which is used to drive the modulator should be exactly the same as every integer corresponding integer value that was received at the output. Okay, so we have two inputs. One will be the received one, which is the output of the demodulator, and the other is the corresponding sequence over here, which was used to drive the input to the modulator. Okay, so that's the way we wire them up. Okay, so we're almost ready at this stage. Now we just need to configure these three blocks that we have here, and then we just need to look at, well, how do we get at the numbers and what do they mean at the output of the error rate calculation block. So if I firstly go to the constellation diagram, we just have to reconfigure it. If I just open this one, okay, so there is our transmitter constellation diagram. Now we just need to configure it to align with what we're simulating in the model. Now, as you can see, at the moment, we have 4 dots, or 4 crosses in our constellation diagram. So it's clearly not a 16 QAM, it's simply a QPSK diagram there. Now, the way we can configure it is if we go to View and the Configuration Properties, okay, the reference constellation is the one we want here, okay, and we want to drag that down to 16 QAM is what we're using. So we can see immediately our diagram changes now to what you would expect, a 4x4 matrix of constellation points. Okay, we got to align our normalization with the one that was used in the modulator and demodulator, which, if you remember, was peak power. So that's kind of just the scaling of the amplitudes. Okay, so I'll apply that. Now, the other thing I want to display or configure here is I'm going to end up, in a few moments we'll show it, running the simulation here. And the simulation will effectively model what happens if I could run my random integer generator through a process of generating several thousand different integer values. Okay, and I'd like to, at the end of the process, to have kind of a visualization here of the actual transmitted signals on the transmitter constellation diagram and the equivalent receiver constellation diagram. Okay, so I want to change this particular parameter here. Okay, and I'm going to enter a value of 1000. Now what this value does is it indicates what's the how many points, each representing an individual symbol that's transmitted or received, do we plot on this diagram. So if we configure this to 1000, it'll plot 1000 points maximum, and then it'll refresh the diagram. Okay, so if I run my simulation for several thousand points, okay, I don't want the diagram to get too cluttered up with a dot on the diagram for every single simulated um, symbol. Okay, I want a maximum of 1000. Otherwise, your diagram might get a little bit cluttered. Okay, so I'll do that and I'll save that now. And that's my transmitter constellation diagram. If I do the same for the receiver constellation diagram, just to configure it. Okay, so again, view configuration properties. And the same thing. Okay, I need to change this to 16 QAM. So again, the background you can see there now, I've got the right constellation pattern, and change it to peak power because that's what we were using and we configured for our modulator and demodulator. Okay, and then similarly with the main subtab, I'll do the same thing. I want as it were this particular plot to refresh or to have a maximum of 1000 dots on it. Okay. You see the relevance perhaps of this a little bit clearer now when I actually do run the simulation. All right, so that's the two transmitter and receiver constellation diagrams correctly configured to align with the 16 QAM and the normalization that's used in the modulator and demodulator. Okay, now as I said, the core aspect of this simulation is you run it to simulate or to model several large number of symbols. Okay, each symbol will be fed through the modulator, noise, demodulator process, and we compare whether our receiver ends up receiving the same integer value as our transmitter transmitted. Okay, and our error rate calculation then. Okay, we need to configure it, we need to understand what it represents. Okay, so if we click open the error rate calculator, we'll see a couple of parameters in there. Okay, now we can leave most of these alone. Okay, the one we do want to change, however, is this output data. Okay, so this particular parameter, it describes where the results are actually stored. So our error rate calculator will basically, as the name suggests, it will calculate the error rate. Okay, and by default, it outputs that calculated value, and that's not the only value, we'll come to that in a second, that it calculates to the workspace. So basically, it'll create a variable in MATLAB which contains the results of the calculation. Now, I don't want to do that here. I want to basically be able to see it on the model when I run it. So instead of outputting the data to the workspace, I'll output it to a port. Okay. So when I do that, okay, and I apply it, okay, we'll see that a little arrow now has appeared that wasn't there before. Okay, so in other words, by changing that to port, it basically says that the model block, rather than saving the results of the error rate calculation to a variable in MATLAB workspace, it outputs those as an output of the block. Okay, now I'll need a new block to actually see the results. So if I open again the library browser, and this time I go to Simulink, okay, and I want to go to a sync here, and I want to use this block, the display block. Okay, so again, I grab and drag it out. So the display block is simply used as the name says, to display values. Okay, so the error rate calculator, the output of it is a number of values, one of which is the error rate. So I will feed the output of that into the input of the display block. Okay, and we'll see that when we run the simulation what the display block actually does. It literally displays the values produced by this. Now, there are actually 3 different values that are produced. So in order to be able to see all 3 of them when I run, I'm just going to make that block a little bit bigger. Okay, so that should be everything ready to run the simulation. Okay, now if I go back to my random integer here, okay, I am going to be generating a random integer basically every sample. Okay, if I use the default values. Now I want to run, so here's my button to run the simulator. Now I only want to run it for a fixed amount of time. I don't want it running ad infinitum. So I'll run it for a certain number of sample steps. Okay, I'll have one symbol generated, one random integer over here generated for each sample step. So I'll start off and I'll generate 10,000 symbols, one every sample step. So the number of steps in my simulation starts at step 0. So 9,999 is the stop time. Start time is 0. So that will run for 10,000 steps, a symbol at each step. Okay. Okay, so we're ready now to run the simulator for our configured 10,000 steps. I click on the run button. See, very quickly runs. Okay, so as I previously mentioned, we get the pop-up of our constellation diagram. So we have our transmitter constellation diagram, we have our receiver constellation diagram. Okay, so firstly, let's just look at those 2 values. Sorry, 2 little figures that have been opened. Okay, so if we just make this one a little bit bigger for the moment. All right, so this was our transmitter. Okay, so if we remember, a constellation diagram is just a graphical representation which shows you or summarizes the waveform that has been transmitted. Okay, how much amplitude in the in-phase component, what's the amplitude of the in-phase component, the amplitude of the quadrature component. Okay, so we had our constellation diagram, it's QAM16, so we have 16 points in the constellation diagram. All right, so in our simulation, we had 10,000 steps. At each step, our random integer between 0 and 15 was generated. That would correspond to one of these points on the constellation diagram. Okay, that waveform effectively would have been simulated as being transmitted. Now, when you see it there, you'll see there is a little yellow dot, okay, represented on each of the points on the constellation diagram. Okay, so basically, when we simulated our 10,000 steps, each step involving an integer value, a symbol between 0 and 15, we transmitted it. Okay, and each point would be each transmitted waveform would be one of the 16 constellation points. All right, so not particularly clear here, but there actually are 1,000 yellow dots drawn on this diagram, but they're all drawn on the same 16 points because that's what the transmitter does. It picks one of the 16, depending on what the integer value was that was fed into the input of the modulator block. It transmits a waveform based on that. So it's the same 16 points that are always being transmitted. Okay, the same waveform in terms of its amplitude in the in phase and the quadrature component. Okay, now it's a little bit more obvious when we look at the received one, which is over here, what's going on. Okay, so now we can see this is the received signal. Okay, so we now see that you can just about make out the 16 red crosses are still there representing the points on the constellation diagram. But remember, they represent the ideal transmitted waveform. This constellation diagram is at the output of the channel, so noise has been added in. So even though all of our points would start at one of the 16 possible points on the constellation diagram, because of the noise that the channel has added, the received signal is not at those points. You can see that it has, as it were, drifted away from it. Okay, so there's different ones, for each of the 16, you can see there's a plot. Okay, now we configured our constellation diagram. I just go back to it here. Again, this is where this 1,000 values come in. Okay, so in any given go, there are only 1,000 of these yellow dots drawn. Okay, and then it refreshes with another dot and gets rid of one. Okay, so there in total there are actually 1,000 yellow dots on your diagram there. Okay, randomly there's 1/16 of 1,000 on each one, uh, uh, surrounding each of the constellation points. But it illustrates there the fact that when you're talking about receiving, okay, you will not be receiving a signal that's exactly the same as what was transmitted, which would be exactly on the constellation point. It has drifted a little bit because of noise. Now, because of our signal to noise density, which as I said at the very beginning is quite low in this case, they haven't significantly drifted. And you can see we have an outline here uh, to show us, help us with the kind of visualize the decision boundaries. But all of the points will say, if I take this point on the constellation diagram, none of them have drifted to such an extent, i.e. the noise hasn't corrupted them to such an extent that they're in danger of going into the decision boundary associated with a different point, which would introduce a bit error. So we've run the simulation here in this case at such a high signal to noise power, energy per bit to noise density, that while there is some noise caused by the channel, it's not big enough that it looks like we would expect to see any errors whatsoever. So I'd expect the number of errors to be 0, okay, for such a simulation, because um, the noise power really was not particularly high. So we get to looking at this display box that I added, and I said there are actually 3 numbers displayed. Now, to summarize the 3 numbers, the bottom number is the total number of steps, or sorry, total number of symbols, okay, which were used in the calculation of the error rate calculation. Okay, this middle block is the number of errors that were detected, and then the top block is the error rate. Okay, now we'll see this a little bit better if I go in here and I reduce down the energy per bit. So I'm effectively reducing down the power compared to the noise. So the ratio of noise to power now is significantly lower. So I should be expecting to see more noise and more errors in this case. So I rerun my simulation. Here it is rerunning. Okay, so that's my transmitted constellation diagram. So no different in that case. That's not unexpected because your transmitted constellation diagram are the waveform that's transmitted for each of my symbols, each of my integer values that are fed in, and they should be exactly on the constellation diagram. But the more interesting one now is the received one, because now we can see that the received point, the yellow dots, are far further away from where they started, which would be each of the 16 crosses. Okay, why? Because the noise relative to the power of the signal is much, much higher, or the signal relative to the power of the noise is much, much lower. Okay, so they have become more spread out, and now some of them are spread out so far that you'll start to make errors. Okay, that we will incorrectly think that a bit which started at, we'll say this red cross here, so much noise was picked up, and maybe this dot here has crossed over into the decision boundary. And what that would mean is that the integer value, which was which was the input value, is now going to be incorrectly received. The demodulator will think it's a different integer value that was being transmitted. Okay, so I expect now to see some non-zero values in my error calculator. Okay, and if I go over, I do see that. I see that 523 of the integer values were different between the output of the demodulator and the input to the modulator. So the process of modulating and specifically passing it through the noisy channel has resulted in 523 of the 10,000 symbols being received differently to how they were transmitted. And the top value then is the error rate. Okay, it's 523 over 10,000. Now, very important thing. this error rate here. What error rate is it? Is it the bit error rate or what is it? Okay, well, remember we're operating at symbol level here. We're comparing the integer value over here that was used as input to the modulator to the integer values outputted by the demodulator. So this error rate, the 0.0523 error rate, is the symbol error rate. It's not the bit error rate. Okay, so basically 523 of the 10,000 symbols have been received in error. Generally, we're more interested in knowing the bit error rate, not the symbol error rate. Okay, so the question then becomes, how do you convert between the two of them? Okay, it's symbol and bit error rate. Okay, so if you think about it, if I get a symbol wrong, question is how many bits are wrong if I get a symbol wrong. Now this is where kind of the gray code comes into it. Okay, if you remember here, we configured this as gray. Same in the modulator, same in the demodulator. Okay, so if you go back to your constellation diagrams, okay, you'll see that in the notes that there's a 4-bit, of course, code associated with each point. Okay, now the question is, how do you assign each 4-bit code to each point? And of course, in general, there's nothing to stop you just arbitrarily assigning each unique 4-bit code to each one of the 16 points of constellation diagram. However, if you do it in a sensible way, using what's called the gray code, it will mean that directly adjacent points on the constellation diagram, only their 4-bit codes only differ by 1-bit value. Okay, so if I compared two points that are right beside each other on the constellation diagram and looked at the 4-bit values for each of those 2 points, they would only differ by 1 bit. Okay, so when we're running our simulations here, okay, and this will be a fairly accurate assumption, okay, what we're basically going to be saying is that anytime we have a symbol error, okay, it means that we have, if I go into my constellation diagram again, okay, we're basically saying that the noise has moved our transmitted point on the constellation diagram, the red arrows, to one of the adjacent, directly adjacent decision boundaries. Okay, and that assumption is going to be quite valid unless you go and do very, very large, large noise powers, relative signal power. So go in and change your energy per bit to noise power to a very, very small, a very, very low value, a negative value. Okay, if you run it at very, very large negative energy per bit to noise density in decibels, then you're simulating huge amounts of noise, which could move your simulation, your simulated transmitted point to another decision boundary that's well beyond the directly adjacent boundaries. But as I said, if you keep those energy per bits of noise to relatively acceptable values, then it's a reasonable assumption to basically say that one symbol error corresponds to 1 bit error. Why? Well, you're basically saying that you will have moved from the constellation point you transmitted at, i.e. one of these 16 values, okay, here, into a point which would be classified as being in one of the directly adjacent neighbors of it. Okay, so they will only differ by 1 bit value. All right, so that's the assumption we're going to use when we go from knowing what the symbol error rate is to the bit error rate. Okay, so in this case, if I have a symbol error rate of 0.0523, so in other words, ballpark 1 in every 20 symbols are errored. Okay, so our symbol error rate is 5 out of every 100 symbols. All right, now every symbol in this modulation scheme is a 4-bit value. Okay, it's representing 4 bits. All right, so 5 out of 100 symbols, okay, is 5 out of 400 bits. Okay, so 5 out of 400 bits, the bit error rate is much, in terms of a numeric value, our bit error rate is equal to the symbol error rate, 0.0523, divided by 4. Why 4? It's 4 bits per symbol when it's 16 QAM. All right, so the symbol error rate, which is displayed here, we convert that to the bit error rate by basically dividing the symbol error rate by the number of bits per symbol. Okay, so that's how we can calculate the bit error rate from our simulator. Okay, so as I said, we can go in and we can just initially play with this a little bit. All right, so we ran it at 10. No harm in rerunning it again at 10. Okay, we can see that there was quite a lot of noise. We go to the received one, quite a lot of noise, causing some bit errors, quite a number. If I run it at 15, what do I expect? Well, remember, 15 is the energy per bit, 15 decibels the energy per bit. So we're basically saying there is more energy per bit now in this simulation relative to the noise than there was in the last one. Okay, so we should expect to see less of an impact of noise. So again, you can see here they're more in the received constellation diagram. They're still spread out because of the noise, but they're not as spread out as in the previous simulation. We'll see that there are some bit errors, but it's much, much less. Okay, and if I do it again at an even higher power, let me go to 25 decibels. Okay, and run that. This time again, I should see again what I expect to see. 25 dB is saying I've even got more signal to noise. All right, so the impact of noise is again reduced down even more significantly. You see they're still spread out, but very little movement away from the constellation diagram. Some, but very little. And again, you can see you can see none of the yellows dots in this plot are anywhere close to the decision boundary, so I'd expect to see 0-bit error rates. That's what I see there. Okay, so that's the basic idea of simulation. Now, a couple of things. In the assignment, you're asked to look at a whole range of energy per bit noise density or power efficiency values. Okay, now you need to run your simulation for a sensible amount of time. Okay, I didn't see any bit errors there. Okay, but if I'd run the simulation for longer, if I ran it for 999,999 steps, I might. If I'm only expect to see 1 in a million bit errors, okay, or 1 in a million symbol errors, because again, remember the value that's produced here is the symbol error rate. Okay, you've got to be sensible about how long you run your simulation for. If I'm only expecting 1 in a million symbol errors, then I got to at least simulate a million symbol errors to even expect to see one of them. All right, so you can't be running it for 9,999, 10,000 steps. That's only 10,000 symbols. If you're only expecting to see 1 in a million symbols in error, you're not going to see any. So you will need to change that runtime if you're expecting to see very few, very, very low symbol error rates. All right, so that's one thing you need to be doing in your assignment, in doing this assignment, is making sure and noting it in the report how long you ran your simulation for. And that needs to be carefully in terms of the steps, how many steps you run for. That, of course, needs to be based on what you expect the symbol error rate to be. So go back to the equations in the lectures to do that. Okay, what happens when you want to change the QAM scheme from being 16 to 32? Well, there's quite a number of things you're going to have to change here. So if we go through the process, firstly, okay, I'm going to be QAM 32 now. So I'll have 32 points on my constellation diagram. So I want to drive my modulator not with just values between 0 and 15, but 0 and 31. So I need to reconfigure my set size for my random integers to go through all possible integers between 0 and 31. So that's step 1. Step 2, I need to change my modulator to indicate that it's 32 QAM. Okay, so apply that. I need to change my constellation diagram, configure properties, so that it's the 32 QAM constellation diagram. Okay, don't even have that, so I need to use, let me go and I'll change it to 64. Okay, so rather than 32, we'll run with 64. Back here, change that to 64. Okay, Gaussian white noise, again, you're configuring it to run in this energy per bit to noise density mode. So this is our value, our power efficiency value. But to simulate the noise correctly, we have to specify how many bits per symbol. So it's 64 that we're now going with. Okay. So 64 is 6 bits per symbol. Okay. We go back here. Of course, I forgot to reconfigure that to 64. Okay. Apply. My demodulator has to be configured to 64. Apply. My constellation diagram, again, if I go on view, constellation, go to the reference, 64, I can, if I want to do 32, I can go in there in the user defined one and do it there. Okay, I'll close that. I've done the demodulator and that's it then. Yeah, that should be it. So I can rerun that. I'm going to run it at the same 25 dB that I ran like 16 QAM a few minutes ago. And this is to illustrate, you know, what we talked about in lectures. If you try to go with a higher order QAM with the same power efficiency, you should expect to see more bit errors. Okay, because why? And if I go into my diagram here, the constellation diagrams, they're closer, the points are now close together. It requires less noise for an error to happen. Okay, so I'll run my simulation diagram. Hopefully I've remembered to change all the bits. Looks like I have. Okay, here's my transmitted one. Again, there is a yellow dot at each one of the 64 points. In fact, there are multiple yellow dots all at the same, drawn on top of each other, because I have simulated all 64 during my 10,000 symbols. All 64 have been generated. Okay, here we can see our received constellation, and we have indeed here can see that all 64 have been exercised. Okay, we've got, even though we have the same energy per bit noise density, okay, so we have absolute terms the same spread of received in terms of how they receive signals are centered around the spread out around the point that we're transmitted at. We can now see that because the 64, we have 64 points in our constellation diagram, it requires less noise for you to drift into an adjacent decision boundary and hence introduce a symbol error. Now it doesn't look like we've had enough energy there to cause any, but at least we've run it correctly. Okay, and indeed we can see our bit error rates there have not reduced, have not caused any symbol errors at all. So because I haven't run it for long enough, okay. If I had ran it for maybe 100,000 symbols, I might have got one. Okay, but let me just quickly reduce down to 20 dB the energy per bit to noise density. Okay, so there's my transmitter. Let me close it. My receiver one. Okay, a bit more spread out. Hopefully we'll have an error. Yeah, so we got 8 symbols out of the 10,000. So my symbol error rate is 0.0008. Okay, what's my bit error rate in this case? That's the symbol error rate. How many of the integers were different between what was transmitted and received? It's 8 out of 10,000. Okay, what does that correspond to in bit error rates? Well, our reasonable assumption is it's 1 bit for every symbol that was wrong. We have 1 bit error. So the bit error rate is the symbol error rate of 0.0008, okay, divided by the number of bits per symbol, which with 64 is 6 bits per symbol. So it would be 0.0008 divided by 6 to give us a bit error rate. Okay. All right, so the rest of the assignment is really all about just using this model for different power efficiency values, so changing the energy per bit to noise density value here through a range of values, okay, and noting the results, plotting them at the end of the day, and also going through the process of different orders of quadrature amplitude modulation. Okay, 16, 32, 8, 64, and so on, and looking at how it impacts on the thing, on the performance of the modulation scheme. As I said, you need to be very, very clear in your head about the relationship, okay, that this value here is the symbol error rate, and it's symbol because it's comparing the integers that were transmitted here to the integers that were received over here. It's not bits, it's symbols. So this value is the symbol error rate, but to convert it to a bit error rate, the reasonable conversion is to divide the symbol error rate by the number of bits per symbol, which of course depends on what form of QAM you're using. Okay, so that's it. So you just go through that process. The final part of the assignment then is a little bit of research to look at the more sophisticated models that are available. So if I go back in here, we're not going to use them. They're not expected to use them. Okay, but if you go into the channel here, you will see under this SISO single input, single output, you have this distribution called, it can either be, a Rayleigh, or it can be a Rickian or a Rayleigh distribution. So a little bit of research as to what is the limitations of the model we use, okay, the additive white Gaussian noise model, and what's more realistic about using a fading model, okay, a Rayleigh or a Rickian fading model. What in terms of real, for example, radio communication link, which is a very common example of where you find digital modulation in the world today, whether it's on mobile, between mobile and base station, or between Wi-Fi node and the Wi-Fi access point. What's more realistic about Rickian and Rayleigh, Rayleigh or Rickian? Okay, what's fading, in other words? And would you expect to see it in things like short range Wi-Fi, or would you expect to see it in longer range communication links? So how realistic is the model that you're using? Okay, so finally then, when you're finished at least developing the initial model, of course you always want to save your work. Okay, so you go up to save, very, very simple, straightforward. You enter your a name for your file, your Simulink file. Okay, now you do have to maintain the MATLAB naming convention here. There are certain characters that it won't accept, as far as I recall. It'll accept an underscore. It won't accept spaces or dashes. Yeah, so that's just saving it. You can zoom in and zoom out if you need to. So just click on the zoom function. Okay, so you can see here I can zoom in. If you want to zoom out, you can use this fit to view button. It'll just zoom out. There we go. And you get back to it fitting exactly into the view. Okay, so that's about it. You should be able to go ahead now and start working on the assignment. Okay, so I just decided to do a quick video here after having some discussions with your class rep this morning because come to the conclusion that the way I had part B and C, well, primarily part B, as impacts part C of the assignment written, it wasn't as clear as it should be. So I wanted to clear up a couple of things, and I've actually rewritten part B and by impact part C of the assignment. Now, the first thing I would say is that if you have already completed the assignment and the report written, or more particularly if you completed parts B and C, regardless of whether it's report written, you don't have to redo it and follow the new instructions. If you want to proceed with the old instructions, you're happy to do so and write up the report that way, that's absolutely fine. You can submit it and it'll be marked based on the original assignment description. Okay, I'll have a separate submission mechanism in Blackboard for the original. Okay, if you haven't done it yet, the assignment, I would strongly recommend you use the updated instructions that I put up today, which has the new updated part B and part C. I think it clarifies things an awful lot more what's required. Okay, so get to the crux of what I wanted to cover in this video. Well, two things. Okay, firstly, I just want to reiterate something I distributed by email last week, I think it was. Okay, that in the notes, and you will use this in the assignment particularly, we have these equations, okay, and particularly as the assignment is based on QAM, you have this equation here, which allows you to plug in power efficiency value gamma, and it gives you, as is indicated here, an approximate bit error rate. Okay, now the reason why it's described as an approximate bit error rate is because it's based on a derivation where the derivation concludes with a symbol error rate, okay, and we then imply the bit error rate from the symbol error rate by making some very, very simple assumptions, and those assumptions are valid except if you start to go to very low power efficiency values where the level of noise is, broadly similar or close to the error, the noise is close to the actual error energy per bit. Okay, the equation that's in the slides there actually more correctly, and I would have always used what's in front of you here, which is from the 2019 exam paper. The equation split into two steps. Okay, the first step, which is based on the theory, which allows you to go from the power efficiency to the symbol error rate, and step two then is to go from the symbol error rate to the bit error rate. Okay, now I would have indicated that, well, it's a simple, in the case of QAM 16, it's a simple division by 4. Okay, whatever your symbol error rate you get out of the simulation model in Simulink, divide that by 4 to give you the bit error rate, on the basis that every symbol error is caused by 1 bit error. Okay, that's the basis of that. Okay, now the problem is that that is not always a valid assumption. Okay, it will be valid if you have a set of codes like shown in this constellation diagram here, where if we, as I would have highlighted this in lectures, if you take a point, all of its 4 nearest neighboring constellation points, the only difference between the codes between the point in the middle and the 4 neighbors that I've highlighted around it is a single bit error. So the assumption is that, well, what is noise going to do if I transmit this point here or that symbol there? Well, noise will potentially cause it to, as the waveform travels through the medium, it could potentially result, because of noise, in you ending up in one of the neighboring decision regions, and hence you end up classifying what was transmitted to represent 100 as being either 1001 or 1100 or 1010 or 0000. Okay, that they're the 4 most likely places you would end up. Okay, and each one of those 4 has the single bit error, and hence again the 1 in 4
factor. Of course, what will happen is if the noise is quite significant, that assumption will not necessarily be valid. If you have a lot of noise, you could potentially end up here, okay, or here, or here, or here, where you actually have 2 bits different. And with a huge amount of noise, you could end up with here, or here, or here, or here, or here, or here, where you have more than 2-bit errors, or even worst case here, okay, where you have 4-bit errors. Okay, so big enough noise and your assumption of single bit per error per symbol, each symbol is equivalent, error is equivalent to 1-bit error, is no longer valid. Okay, now if you want to get extra marks in the assignment, okay, you'll have to adapt your MATLAB simulation so that for each symbol that's transmitted, you look at the bits that are used to represent it, and then you look at the equivalent 4 bits that are received after demodulation, and you calculate the actual number of bit errors. Okay, but as I said, the equation will be okay until you start going down to low gamma values, low power efficiency values, and the simulation, similarly, of doing the simple symbol error rate divided by 4 will be okay until you go down to low power efficiency values. So either you can steer away from the low power efficiency values and get good mapping between the two, or as I said, for the simulation, you can investigate the low power efficiency values and factor in the fact into your simulation by enhancing it. You track the number of bit errors that are actually occurred in rather than estimating it as a quarter of the symbol error rate. Okay, so that was the first thing. So that was kind of a minor point, just to kind of re-emphasize what I said in my email last week, I think it was. Now, the more substantive issue then, which cropped up this morning, was all around part B of the assignment, which on reflection, having discussed it with your class rep to and fro, really wasn't 100% clear. Okay, in fact, you could almost say it was a little bit misleading the way I had it written in terms of what you needed to do. Okay, so what I would say is if we start off with part A, which is unchanged, okay, you are asked to use QM16 and for a range of different power efficiencies, gamma values, plug them into the equation to give you bit error rates, run the simulation to give you simulated bit error rates, okay, and then to plot the two of them. Okay, so you will end up, again, thanks to your colleague, I have a set of data here of power efficiency and the calculated values by plugging them into the equation and the results of simulation. Okay, now you've got a lot of zeros here in the simulation because you probably have to run the simulation for an extended period of time, because remember, if you're, as I said in the original video, if you're looking to expect to see, as you are here, 1 in a million, 1 in 10 million, 1 in a trillion bit errors, okay, you need to be running at least a million, a billion, a trillion bits through the simulation, and probably a multiple of that to get that 1 in those. Okay, so you know, you have two options here. If you start saying, well, I tried these bit error rates and I didn't get any, is, well, you can extrapolate it graphically from these values that you did get, or as I said, try running the simulation for much longer. Okay, now I wouldn't be going down into these kind of regions where it's minus 11, 13, 16. You'd be running the simulation all day to get those. So I'd be certainly stopping at 10 to the minus 9, even 10 to the minus 7, I think is more than sufficient to stop at. Okay, so you would end up with a set of results there. So let me kind of just go over the region I said that you might want to go with. And I'll just do a plot here in Excel. Okay, a scatter plot. Okay, so there we are, our scatter plot of our data. We've got blues and oranges. You can really only see the blues. Now, what I would like, okay, that's the kind of thing you could plot for part A. If you look at a lot of how this is reported, a small tweak makes it a lot easier to read, okay, and that is to use a log scale for the bit error rate, okay, because you're going from bit error rates that are, as you can see here, 0.1 all the way down to a millionth of that. Okay, linear scale really makes it very hard to see the details if you do that. So a log scale will allow you to see the details a lot more clearly. So you get this type of shape, okay, which is showing how the bit error rate decreases as your power efficiency increases. So it all makes sense. Okay, the more power you use to transmit your signal, the clearer it is, as it were, relative to the noise, and hence the less bit errors you should be seeing. So you should be expect to see that kind of a fall off behavior. Okay, now we then come to part B. Okay, that would have been generated for part A. Okay, now for part B, we're basically being asked to compare power and spectral efficiency. And we want to do that for the real world, which is our simulation model, and the theoretical case, which is given by the Shannon-Hartley equation, okay, which is this equation on the slide here, okay, so this one here, okay, which relates theoretical limit between power efficiency and spectral efficiency for error-free communication, okay. Now, in our simulations and in our calculations, we can see that we always get, for most cases, some sort of bit errors. You would in the real world. Leave it there long enough, you'll get bit errors. Okay, so we can't really capture complete error-free communication. But what we can do for this real, and this was for QAM16, we can set a threshold which we'll say for all intents and purposes is error-free communication. Okay, and we're going to set it to, say, the bottom level there, which is 10 to the minus 7. You could set it to 10 to the minus 6, okay, which I think is this one. If you wanted 1 in a million, yeah, that's kind of close to error-free. 1 in, I think this is 1 in every 10 million is even better, okay? So if we set it to 1 in every 10 million, that's effectively, for all intents and purposes, is error-free communication, okay? And what this graph is telling us is that, well, let me just actually redraw the graph, this time with a spline generated through it. Okay, so let me insert a scatter with a spline through it of some description, and let me change that. Let me change the log scale again to go back and give me my logarithmic scale. Okay, so there we are. We've got a line through it now. Okay, okay, I actually generated all of them, but I'm interested in 10 to the minus 7 one, which is this one. And what we can see there is that if we treat that as kind of error-free communicate, the threshold in the real world for what we'll treat as error-free communication, we can see there that in order to achieve it, we need a power efficiency of at least about 15 dB. It's a tiny bit above 15 dB, but for all intents and purposes, we'll mark that as just 15 dB there, okay, that value. All right, so for our simulation model, we're basically saying it's 15 dB. Okay, so that gives us a value for the threshold for power efficiency for QAM16 in the real world. Okay, so for QAM16, we need at least to be transmitting at 15 dB to achieve what we'll regard as error-free communication. Now, what's the spectral efficiency for QAM16? Well, that's actually given to us in our notes here. Where are we? Sorry. Down here. Okay, you can see there spectral efficiency. Okay, whichever one of the two you want to use there. So QAM16. Okay, let's just go into QAM16. We can see it's a half of log space 2 of m. M is 16 in that case. So plug it in. That gives us 4 divided by 2, which is 2. Okay, so our spectral efficiency for QAM16 is 2. Okay, another way to calculate spectral efficiency, or not another way, but where that equation came from, is the bit rate divided by the bandwidth, and you assume your bit rate is equal to the number of bits per symbol times the baud rate, and your bandwidth is twice 1 over the symbol time, and the baud rate is basically 1 over the symbol time. Okay, so we can replace that with the baud rate. We can cancel our 2 baud rates, and what I'm left with for my spectral efficiency is just the number of bits per symbol divided by 2. Okay, and for QAM16 is 4 bits per symbol. Okay, each of the symbols represent 4 bits. So I have 1 point. Okay, so this kind of is where we want to get to with part B. Okay, what we want to get to with part B is the plot, not now as we had in part A of the power efficiency versus BER, but power efficiency versus spectral efficiency. Okay. Okay, so that's rho. Okay, and now I have a point. Okay, that's 15 dB and 2. Okay, so there's my point. That point is specific to QAM16, my simulation scenario. So just raw bits sent over QAM16. All right, if I do the same for a set of QAMs, so QAM 8 or 4 or 16, sorry, you've done 16, 32, 64, 120. Pick a number of them and carry out exactly the same process, okay, as you've just done. Okay, so generate this type of graph using exactly the same threshold of 10 to the minus 6 or 10 to the minus 7. Find the power efficiency that the graph here tells you. As I said, maybe a point I didn't make there, if you're looking at the simulation results and you don't have values down at 10 to the minus 6 or 7, okay, maybe consider run the simulation longer, maybe try and do an interpolation beyond the points, okay, or just pick 10 to the minus 6 as your threshold in all cases. Okay, but use the same threshold in all cases to give you a power efficiency value. Okay, remember then that for QAM, you have the equation here that the spectral efficiency is the number of bits per symbol, which is different for each of the QAMs. 16 is 4 divided by 2. Spectral efficiency, QAM32 will be 5 divided by 2. QAM64 is 6 divided by 2. Okay, and so onwards. Okay, so you can calculate for each of them QAM32, whatever it might be. As we said, that's going to be 2.5. QAM8, you'll get some value by means of your simulation, and with 8 it'll be 1.5. QAM64, for argument's sake, again, your simulation will give you your threshold for power efficiency, and that will be 3, and so on, 128. Okay, that'll be 3.5, 256, that'll be 4, and you'll have corresponding. Each of those will give you discrete values here on your plot, okay, giving you a representation of a real world, i.e. it's not real world, but it's a simulated world, performance of how the efficiency, the spectral efficiency and the power efficiency are matched, and it's the error-free spectral efficiency in this case. So we've had to look at how big, for each of the modulation scheme, how big do we have to make the power to more or less get error-free communication, okay? In other words, less than 1 in a million bits or less than 1 in 10 million bits are errored. And we get discrete points for each of those. Okay. Now, what we're also asked to do then is to draw the Shannon-Hartley plot on this graph as well. Okay, so that's the graph given by the equation there. All right, so we can draw that graph as well. Okay, and what we should see is something like that. So we know the Shannon-Hartley, it asymptotically goes off at minus 1.6 dB. Okay, never goes any lower than that. But what we should be seeing is our discrete points here for each of the QAM schemes, different QAM schemes, will of course has to be to the right of that graph. Okay, because that's a theoretical limit. You cannot exceed it. Okay, even this absolute floor, the Shannon-Hartley floor here, basically means that, well, as the spectral efficiency, okay, basically goes off to 0 down here. Okay, what's happening to the power efficiency? Well, it's saturating at this asymptotic value. Okay, how does the spectral efficiency go to 0? Well, you might say, well, that means 0 bit rates. Well, no, the other way is, of course, that the bandwidth goes to infinity. So in other words, you're basically saying that in order to get bits across the communication link, you need infinite bandwidth. Why? Well, because there's so much noise. Okay, in theory anyway. Okay, so you'll end up with a plot, as I said, in part B, where you have the plot of this equation, the theoretical, and you have a number of discrete points. How many of these depends on yourself, of course, how many of these different simulations you want to run to get these discrete points. Obviously, you'll have at least a QAM16 one, okay, but you are asked to do more, okay? And you have this gap then between them, for the given spectral efficiency, what's the gap between the theoretical limit and the point you've just measured, okay, the actual implementation. Okay, that's the gap in the power efficiency between how low the power should be in theory to give error-free communication versus how long it is in reality, i.e. the simulation, to get as near as equivalent to error-free communication. Okay, and then there are various techniques, in fact, a lot of which we've kind of looked at in terms of the concepts in second year, that are used to try and get down closer to reduce that gap. Remember, we're not using anything in our simulation, okay, that might allow you to suppress that gap. Okay, we're just sending raw bits, getting raw bits out the other side, but there are techniques that in theory allow you to do that, and you are asked to do a little bit of reading to see if you can come up with what these techniques are, and just discuss them one line or two will do. In part B there, you're asked to do that, what kind of technique could be used. You don't have to simulate them, just say what kind of techniques could be used to bridge that gap. Not completely, but get the real world closer to the theoretical value given by the Shannon-Hartley. Okay, so that's part B. Part C then is just adapted slightly, okay, because in part C you're investigating how the QAM order varies. Okay, now you'll have results for that having had done part B. Okay, you may have the results. You could use the BER value. You should have results for different BER values for different QAM schemes. So there should be little or no need to use to rerun any simulation to do part C. Okay, it's just presenting the data in a slightly different way to examine how the bit error rate for a particular power efficiency, fixed power efficiency, varies with the order of the QAM system. Okay, so that's just hopefully clarifies things a little bit. As I said, if you want to go back and do it as per the original wording, feel absolutely free to do so. The only requirement is I'll ask you to submit it via a different turn-in assignment at the end of the day, and you'll be marked based on the original wording and what you were asked to do, and that's fine. But as I said, if you haven't done it yet, I'd recommend following the new instructions.